After this lesson, students will be able to find the domain and range of a function, plot them as ordered pairs on a graph, and connect the points with a smooth line or curve. Do now. Complete the table of values for a domain of -2, -1, 0, 1, and 2. Pause the movie in order to try this on your own, and resume when you're ready. Well, if the domain is -2, -1, 0, 1, 2, those are the input or x values. So in our table, we can fill in -2, -1, 0, 1, and 2. Next, we substitute those values of x into our equation. So f of -2 equals 4 times -2 plus 1. F of -1 equals 4 times -1 plus 1. F of 0 equals 4 times 0 plus 1. F of 1 equals 4 times 1 plus 1. And f of 2 equals 4 times 2 plus 1. And now we can go ahead and evaluate those. So 4 times -2 is -8 plus 1 gives us -7. 4 times -1 is -4 plus 1 is -3. 4 times 0 is 0 plus 1 is 1. 4 times 1 is 4 plus 1 is 5. And 4 times 2 is 8 plus 1 is 9. Now the input and output values are like the x, y coordinates of an ordered pair. So for example, -2, -7 is one of the ordered pairs given by this equation. -1, -3 is another, as is 0, 1, 1, 5, and 2, 9. Now we can plot these ordered pairs on a coordinate grid. -2, -7, -1, -3, 0, 1, 1, 5, and 2, 9, which will be off of our grid. Now we can connect these with a straight edge, so use a ruler to connect those dots. And draw arrows on either end to show that this line does go on forever in both directions. Now this is a little preview of our upcoming chapter on linear equations, but just so you know that linear equations are graphs of straight lines, like what we just graphed, and that they can be written in slope-intercept form. Y equals mx plus b, where y is the y-coordinate of a point on the line, and the x is the x-coordinate of a point on the line, like these xy coordinates that we found through our table. M is the slope, which is rise over run, and b is the y-intercept, where the line crosses the y-axis. So as a little preview, you can see that the xy coordinates that we found are all on the line, that the slope, m, is 4, which means that to get from one point to another point, we rise 4 and run 1. 1, 2, 3, 4 up, and then run 1 in order to get to our next point. And the y-intercept, which in our case is 1, is where the line crosses the y-axis. Well, here's our y-axis, and our line does cross the y-axis at 1. Model the function rule y equals negative 1/2 x plus 1 using a table of values and a graph. Once again, we can use the input values negative 2, negative 1, 0, 1, and 2. And then we can go ahead and substitute those x values into our equation. So y equals negative 1/2 times negative 2 plus 1. Y equals negative 1/2 times negative 1 plus 1. Y equals negative 1/2 times 0 plus 1. Y equals negative 1/2 times 1 plus 1. And y equals negative 1/2 times 2 plus 1. So our x is negative 2. Our y, we begin with multiplication. Negative 1/2 times negative 2 is positive 1, plus 1 is 2. Our x is negative 1. We multiply negative 1/2 times negative 1 in order to get 1/2, plus 1 gives us 1.5. For 0, negative 1/2 times 0 is 0, so we add 1 to that and get 1. With 1, we have negative 1/2 times 1, which is negative 1/2, plus 1, which gives us 1/2. And finally, with 2, negative 1/2 times 2 is negative 1, plus 1 is 0. Now we can plot these points. Negative 2, 2, negative 1, 1.5. So I plot that point halfway between the 1 and the 2 on the y-axis. 0, 1, 1, half, and 2, 0. And then we can connect those points with a straight edge. And arrows on either end. Now in this case, we did keep our input values as negative 2, negative 1, 0, 1, 2, which I like to think of sometimes as the default domain, just like your computer might have a default font that when you enter into a Word document, that's the font that is initially chosen. Though sometimes you may consider changing the domain. In this case, it was okay that we had halves because those are easy to graph on a coordinate grid. But in the future, you may want to consider, instead of having the negative 1 and the positive 1, which give you those halves, then instead you could choose values like negative 4, negative 2, 0, 2, and 4, where you won't have to deal with any of the halves. Now to finish up this slide, our rise over run in this case was negative 1 over 2, and as you can see, if I choose a point and I go down 1 for my rise, my negative rise, and then I go 2 to the right for my run, it does lead me to another point on the graph. The y-intercept was our 1, and as you can see, our line does cross the y-axis at 1. You try this one on your own, and consider what I mentioned about not choosing negative 2, negative 1, 0, 1, 2 for your domain. Look at what you're going to have to multiply by and see if you can figure out a better choice. Pause the movie and resume when you're ready. So in this example, while you could choose negative 2, negative 1, 0, 1, 2, I think it would be easier to choose negative 6, negative 3, 0, 3, and 6, which are all multiples of this 3, so that I can not deal with fractions and decimals in my ordered pairs. So here we go. I have y equals 2 plus 1/3 times negative 6. Now we always start with multiplication here because of order of operations. So we're going to do 1/3 times negative 6 first, which gives us negative 2. Negative 2 plus 2 is 0. So negative 6 comma 0. Now we substitute our negative 3. We multiply 1/3 times negative 3 to get negative 1, and 2 plus negative 1 is 1. Next, we substitute 0. 1/3 times 0 is 0, plus 2 gives us 2. Substitute 3. 1/3 times 3 is 1. 1 plus 2 is 3. And finally, we substitute in 6. 1/3 times 6 gives us 2, plus 2 is 4. And now we go ahead and plot those ordered pairs. 1, 2, 3, 4, 5, 6 to the left, and 0 on our y. Negative 3, 1, 1, 2, 3, 1, 0, 2, 3, 3, and 6, 4. And then we can connect those with a straight edge. You can see that by choosing negative 6, negative 3, 0, 3, and 6, I didn't have to deal with fractions and decimals, which was also nice when graphing, and I got a nice spread of the points that crossed through our coordinate grid and weren't just clustered together in one area. Try this question on your own, so pause the movie and resume when you're ready. In this example, a domain of negative 2, negative 1, 0, 1, 2 would work just great. We can substitute those numbers in and solve for y. And then we plot our ordered pairs. Negative 2 comma 4. Negative 1, 2, 0, 0, 1, negative 2, and 2, negative 4. And then we use a straight edge. And then the question also asks, what is the y-intercept, or b, of this graph? Well, if we look at our equation, y equals mx plus b, we can see our y's line up, the equals line up, our m is negative 2, the x's line up, and then there's nothing else, which means that we're adding 0. You can also see on the graph that our line crosses the y-axis at 0, so our y-intercept is 0. Now, not all equations are linear, and therefore, not all graphs make straight lines. So while the examples that we've done so far have been linear, let's try a few other types of graphs. For example, let's graph the function y equals absolute value of x. So let's begin with our domain and substituting those in. And then we calculate our y, so the absolute value of negative 2 is positive 2. Absolute value of negative 1 is positive 1. Absolute value of 0 is 0. Absolute value of 1 is 1. And absolute value of 2 is 2. So now I can go ahead and plot these points. Negative 2, 2. Negative 1, 1. 0, 0. 1, 1. And 2, 2. And then we go ahead and connect those dots. Notice that while this didn't create a straight line, it created a shape of a V. Absolute value equations create graphs that look like the letter V. Let's try another one to see if it creates another V. Graph the function y equals absolute value of x plus 1. You try this on your own, so pause the movie and resume when you're ready. Go ahead and input your domain. Absolute value of negative 2 is 2, plus 1 is 3. Absolute value of negative 1 is 1, plus 1 is 2. Absolute value of 0 is 0, plus 1, which is 1. Absolute value of 1 is 1, plus 1 gives us 2. And absolute value of 2 is 2, plus 1 gives us 3. Plot those points. Negative 2, 1, 2, 3. Negative 1, 2, 0, 1, 1, 2, and 2, 3. And then we can connect those dots. And you'll see that it does create another V. In fact, this graph looks very similar to the previous one. The only difference is that this plus 1 caused the graph to shift up a point. So instead of our vertex, or this corner of the V, being on the origin, it is now 1 up. So these examples, as mentioned, are called absolute value graphs. And the way that I like to remember the shape they make is by using this visual of thinking of value as a V. And that's a reminder to me that I'm not going to get a straight line, but rather I'll get a V shape. Now let's try a different type of graph. Graph the function y equals x squared. We can input negative 2, negative 1, 0, 1, and 2. Now be careful with these because x is being squared. And x in this case is negative 2, meaning that entire quantity is being squared. And therefore it's essential that you write the negative 2 in parentheses. Same thing with negative 1 being in parentheses, and then once we get to 0, 1, and 2, the parentheses become unnecessary, though you can write them if you feel more comfortable. Now we can go ahead and simplify. So negative 2, that entire quantity squared, is negative 2 times negative 2, or positive 4. Negative 1 times negative 1 gives us positive 1. 0 times 0 is 0, 1 times 1 is 1, and 2 times 2 is 4. Now I can plot these ordered pairs on the coordinate grid. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Now notice how this did not create a straight line, and it didn't create a V either, because there is some curvature to this. So when you connect the dots, you should see more of a U shape. Try to graph this function on your own, so pause the movie and resume when you're ready. You can use our default domain of negative 2, negative 1, 0, 1, and 2. Substitute those in and be sure to use those parentheses. And this time I'll be using parentheses on all of them since I am going to be multiplying afterwards. So this is our symbol for multiplication when there's no sign there and just parentheses. Now we always have to follow order of operations. I can't do anything within the parentheses, so next comes exponents. Be careful because the only thing that is being raised to the power of 2 is the negative 2. So I begin by doing negative 2 squared, which is 4, and then multiply by 3 to get 12. A common mistake would be for students to multiply 3 times negative 2 to get negative 6 first, and then try squaring that, which would give them 36. Now, let's do the next one. Negative 1 squared is 1 times 3 is 3. 0 squared is 0 times 3 is 0. 1 squared is 1 times 3 is 3. 2 squared is 4 times 3 is 12. Now we can go ahead and plot these on the coordinate grid. And we are going to run out of space, so we can change our graph to go by 3s. So in other words, we'll count negative 2. Actually, we can just expand our graph a little bit, so that should be okay. We'll do negative 2, 12, because I do want to see the whole effect here. I want to show you that. So negative 2, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 would be all the way up top. Negative 1, 3. 1, 2, 3. 0, 0, 1, 3, and 2, 12, again, which is all the way up top. So you'll notice that this U is a very skinny U, but we do need to be careful to curve that bottom and not make it look like a pointy V, because this is not an absolute value graph. So notice how this time we have a very skinny looking U-shaped graph. The way that I remember these is that each of the examples you'll notice had x squared in it. X squared has a U in it, so it does make a U-shaped graph, and these graphs are called quadratic. So we've had linear graphs, we've had absolute value graphs, and now we have quadratic graphs, which have an x squared in them and make a U shape, which you'll learn later is called a parabola.